Okay, so we can start the last class of this design and analysis of algorithms. After this, there will be no class. So for the exam, you will be having questions from approximation algorithms. Okay, that we'll be discussing today. Then NP completeness question will be there. Okay. Then as usual, this asymptotic analysis, and recurrence. Okay, will be there. Then greedy and dynamic programming will be there. Then randomized algorithm will be there. Okay. Then this the last say 10 classes are very important. Last 10 classes you should follow properly. For my case, last 10 classes. Okay. So, and this is not limited to this. These are, say, this greedy was the new topic, dynamic programming was the new topic. So, question you should be expecting from this, from the midterm. These are new, relatively new. Approximation, NP completeness, relatively new. Okay, so graph algorithms, we are having questions. Graph algorithms. This is also new. Okay. So we should have question on graph algorithm. Randomized algorithm new. So this graph randomized algorithms, you should be expecting questions. Okay. So maybe one question from greedy, one question from say dynamic programming, or combinedly you could have two questions. Maybe approximation NP completeness, you can have one question. Here you can have one question. 3, 4 randomized algorithm, one question. 5 graph algorithm, one question. 6. Okay. So this then we discussed last 10 classes. Whatever I have discussed, you should follow those topics as well. Okay. Right. Okay. So these are questions that are important. Okay. Apart from this, I am not telling that question will be confined to only these. Maybe one question might be they are combining all concepts. Okay. Whatever is taught, right? So this amortized analysis and all these things. But these are main topics which you have to follow. Okay. Right. Last 10, 15 classes you should follow. Okay. Very minutely. Okay, and then whatever is taught in this greedy dynamic programming, then NP completeness you should study. Approximation algorithm will be studying today. Okay. Okay. E add to the next page, and then I should remove this. Okay. Okay, so today this is the last class, and we should study these approximation algorithms. Okay. Just a minute, it's a little bit slow going. Mm, okay, approximation algorithm we should be studying. And here we will be studying one problem called vertex cover. Okay, so you have got the idea of this vertex cover in NP completeness perhaps. But anyway, we will be discussing what this vertex cover is. So even if you are not even if you haven't encountered that in NP completeness, then we can do this. Okay, here. So everybody, is this screen visible to everybody? Can anybody answer that whether this screen is visible?
Yes, sir.
Ah, okay. So now we have got one chapter called NP completeness. Okay, right. NP completeness, and in this chapter, this is at the heart of computer science. Okay. Why? Because this chapter classifies that which problems are hard to solve and which problems are relatively easy to solve. Okay. How we measure? We measure that, okay, if for a problem we are having order of n power k, where k is constant, n power k time algorithm, say order of n squared, where k is 2, k equal to 2, or order of n cube, k equals to 3, then we say that that problem is polynomially solvable. Polynomial polytime algorithm existing for that problem. Polytime algorithm. Okay. Now, whenever say polytime algorithm existing for that problem, we can. So what we have got, say polytime algorithm existing. So can you name one such problem where you have seen polytime algorithm existing? Say order of n cube, or order of n log n, or order of n time, order of n square. Can you name one such problem where we have got the complexity as order of n or order of n log n? Have you seen any algorithm which is running in order of n time?
So linear search.
Linear search. Yes. Linear search order of n time algorithm. Can you name another algorithm which was discussed in the class? Order of n time. So can you
Say
remember
kth
this
smallest number.
kth smallest element finding element algorithm? Okay.
So majority element.
Majority element we have found one. Okay. Order of n. So we have seen lots of problems which are solvable polytime. Okay. Polytime. Right. Now there are problems for which we have tried over a long time, but still we haven't found any polytime algorithm. Polytime algorithm is yet to be discovered. Is yet to be discovered. You see that I haven't used the word that polytime algorithm not existing for those problems. Okay, the polytime algorithm is yet to be discovered. We are trying for over say 70 years of time, but with the brilliant mind, but they are not being able to find out any such. Okay, right. So, but we haven't proved yet that, okay, we haven't found yet any such polytime algorithm for those problems. Say one such problem is traveling salesman problem. Okay, traveling salesman problem. One such problem that we'll be discussing is this vertex cover problem. Okay, so there are other problems for which the polytime algorithm is not known yet. But we are not claiming that, okay, in future somebody might not be able to find out. Okay, there is a famous for this. A famous problem is already there in the computer science parlance, that whether p not equals to np. P means those problems for which we have found polytime algorithm, and np means it is not it is this n is standing for non-deterministic. Okay, non-deterministic non-deterministic polynomial. Okay. That means those problems which are hard. Okay, if if at some point of time somebody proving that, okay, this is not possible at all, nobody, whatever you try, but you cannot find polytime algorithm for those problems, but we couldn't prove that. Okay, so we have to classify those problems which seems harder. We have introduced a concept called non-deterministic polynomial. Okay. And in this non-deterministic polynomial, polytime algorithm also existing. Okay, hard problem also existing in this non-deterministic polynomial class. Okay, but those are the problems which are polytime. We have seen out of those problems, some problems are polytime solvable, and some problems such as traveling salesman's vertex cover, we are not being able to find out any polytime algorithm. So the question we are asking that whether this P not equals to NP. Okay. That means all the problems which are there in this NP class, for all those problems, can we find polytime algorithm? That is the biggest question. Okay. And this is a $1,000,000 question problem. The Clay Mathematics posting say 10 millennia problem. One of the problem is this P not equals to NP. Those who will be discovering that okay, P not equals to NP or P equals to NP, he or she will be famous overnight. Okay. So this is the story. Now we'll be discussing this vertex cover problem. Okay. So what is this vertex cover problem? A vertex cover of an undirected graph G is a subset of vertices V prime is a subset of vertices of this original graph consisting of V vertices such that if UV belongs to this edge E, E means the original graph, okay, then U will be belonging to this V prime or V belonging to V prime or both will be belonging to V prime. In English language, the problem is that each vertex covers its incident edges. And a vertex cover for G is the set of vertices that covers all the edges in E. Okay. The size of the vertex cover is the number of vertices in it. So let us take one example to understand this. Now take this graph. Okay. We have got a graph like this. With this graph, we have almost this structure. We have discussed many graph problems. Okay. Say this graph. Okay. So what is V here? The number of vertices A, B, C, and D. Okay. Right. And say I am telling that out of this V, I am taking one V prime set as A and C. Okay. So now you see this. If I take this A and then this C. Okay. So whenever I am taking this A, now you see this is covering the edges incident on. So which are the edges incident on this and this? So I'll be telling that this vertex A is covering these edges. Now if I am taking, so you see how many edges we are having in the graph? 1, 2, and 3. And out of these, how many covered? This and this by this vertex. But still we are having one edge here. Okay. One edge here. Now to cover this, I have to include this, say, this C. Oh, 1, 2, 3, 4 edges I am having. 1, 2, 3, 4 edges I am having. Okay. So these two edges are yet to be covered. So that can be covered whenever I will be including this C vertex in this set. Okay, because this edge is incident on this edge, and this edge is incident on this. Okay, so these edges are now covered. Okay, so if I include A and C, that will be covering all the edges in this original graph G. Okay, that is, it is covering all the edges of this edge set E. Okay, now we can say that V prime could be A, B, and C also. These vertices, if I include, then A is covering this edges, C is covering these edges, and D I can redundantly I can take it into this. Okay, so like this way, or I can think of that. Okay, with A I have covered up these two, and then when B is included, I have covered this, and when C is included, I have covered this. So with ABC, I can cover all four vertices. So V prime here, V prime is also a subset of V, and this V prime is also a subset of V. Now you see, in this V prime, we are having two vertices. Here we are having three vertices. So the problem is the vertex cover, the size of the vertex cover is the number of vertices in it. Okay, so this V prime having three vertices, this V prime having two vertices. So this is the size of this vertex cover. Now the vertex cover problem is to find the vertex cover of minimum size. Okay. So we are seeing that this V prime, if I am considering, then that is the minimum vertex cover. We can consider another that is this D and B. So that is also a vertex cover. So D and B. This because D set, sorry, D vertex covering these edges and B vertex covering these edges. Then we will be covering all the edges of E set. E is the original in the original graph. How many edges are there? That means 1, 2, 3, 4. There is 1, 2, 3, 4. Okay, this is the original graph. So this is the vertex cover problem. And the big statement is that this vertex cover is NP complete. Okay, is NP complete. So so this is already proved NP complete. With this statement, with this proposition, okay, we'll be proceeding that okay, vertex cover is NP complete. Then if some problem is NP complete, okay, if some problem is NP complete, okay, then what to do? The question comes that what to do? What to do in this scenario? The idea is that we can get the say whenever we say that the problem is NP complete, we say that it is for say vertex cover. We have to consider the graph is a very large graph. Okay, large graph, right? Like this, it's expanding ever and ever, say like this. A very large graph we have to consider. Now, for any general graph, that vertex cover is NP complete. But maybe if we can restrict that each of the vertices will be having only two edges, that is emanating from this, okay, exiting from this vertex. Say if I am having the restriction on this graph, then maybe we can find out one polytime algorithm for NP complete vertex cover problem. Maybe I'm not uh, telling that whether we'll be finding it or not. That means if the NP completeness is around the corner, we can think of some restricted instances of that problem, and we can find out some polytime algorithm for this. Another thing is that in the general graph, we can find out a polytime approximation algorithm. So this approximation, if in this general graph, say we are trying to find out the vertex cover, then vertex cover will be having some, as we have seen, the vertex cover minimum, this v prime will be consisting of say the minimum number of edges which are covering all the minimum number of vertices which are covering all the edges. So that is the minimization problem. That is one optimization problem are of two kinds. One is minimization, one is maximization. So vertex cover is the minimization problem. And that will be if I am trying to find out some minimum vertices which will be covering all the edges. Okay. Then we are finding some optimal solution for this. But we have proved that this optimal solution is NP complete. That means no known polynomial time algorithm yet. Then what we can do is we can go for some approximation algorithm. And whenever we have gone, but that approximation algorithm should be having the polytime, we can go for polytime approximation algorithm. Okay. And the vertex set, vertex cover, say v prime, which we will be finding by this approximation algorithm, the number of vertices, we should be compare those number of vertices with this v prime of the optimal solution. Okay. Of the optimal solution. That is the way we measure the performance of this approximation algorithm. But one question might be coming here is that sir, you are telling that okay, this NP complete problem, we don't know any polytime algorithm or any algorithm, polytime algorithm existing for finding this optimal solution. Okay. Now, how can you design this V prime set which is optimal? We don't know any algorithm, but you are telling that we will be finding one. So is it not contradicting your idea that you are putting forward? Okay. So this is the question. This question we have to first understand. Okay. I am telling that vertex cover problem, no known polynomial time optimal algorithm. So that means if you run any general graph, the algorithm which is existing for this vertex covered, some brute force algorithm, if you run, then you might be finding optimal solution, but that will be taking say 1000 years to get the solution. Okay. So how can you measure that solution with this approximation algorithm solution that you are getting? So this is the question. To solve this question, what we will be doing is, okay, we may not be able to find out the optimal solution exactly, okay, but we can find out the lower bound of that optimal solution of lower bound of this optimal solution. That means no matter what algorithm you are designing for this optimal solution, say I am telling that optimal solution for vertex cover v prime will be consisting of two vertices at least, say A and C. Okay. So that is the lower bound. Maybe the optimal solution might be including another one. But this is absolutely, we cannot have less than this, whatever algorithm I am designing. Okay. So that is called the lower bound of the optimal solution. And that with a clever trick, okay, we can deduce this V prime set. Okay. That is the lower bound, right? So that we have to design. Okay, but the trick that will be applicable for vertex covered may not be applicable for traveling salesman problem. So that's why the challenge is coming, and that's why this is the highest intellectual uh, brain mapping will be necessary. Okay, that's why this is not an easy job. Okay, we can understand, say, vertex covered problem, traveling salesman, some scheduling problem. Okay, but if a new problem is coming, we have to think all over again, and we have to find out some clever trick. Okay, so let us understand what is the clever trick for this vertex covered problem. Okay, for finding the lower bound of this optimal solution, and then from that lower bound of that optimal solution, we will be comparing this the performance of the approximation algorithm. Okay, so first we have to take into consideration this approx vertex covered algorithm. Okay, so what algorithm we are designing for this approx vertex covered approximation algorithm? What approximation algorithm we are designing? That we have to understand first. That means that is our algorithm, and that algorithm will be compared. That algorithm will be compared with the soft, or rather this lower bound of right. So try to understand this. This approx vertex cover is a very easy approximation algorithm, and many approximation algorithm is in some sense greedy. Okay. So greedy algorithm comes in a natural way for designing approximation algorithm. Okay. So take this vertex, take this graph G, and we are trying to design the approximation algorithm for any such graph. Okay, it can have the structure like this. Okay, whatever graph we are having. So let us assume that this is the graph. Okay, and the algorithm is this. So what we got to do, consider an arbitrary edge UV from the set of all edges not yet covered. Not yet covered. So the set of all edges denoted by, say, E prime. So now this say this consider an arbitrary edge. So E prime having this say this edge AB, this edge AB, okay, this edge AB, BC, BC, CD, AD, AE, right? So these are the set of edges. And now I'll be considering any arbitrary edge. Say for example, AB I am considering. Now include that edge in the vertex covered set, which are including that edge means the corresponding vertices of that edge, UV. So C was initially null, and now C equal to C union this U and V. Okay. That means in our example U is A and V is B. So C will be, after first iteration, C will be consisting of AB. And now what we got to do is remove from E prime every edge incident on either U or V. That means AB I am considering these two vertices. So all edges incident on this. So first I am taking A, and all edges incident on this I am removing. So these edges we have to remove. And then once I am considering B, already this is removed. So this will be, this is the edge incident on B also. So we have to remove this. Right. So these edges after the first iteration will be removed. Then the graph will be consisting of D and C. We can think of. So now what we can do, we can consider this CD edge. Okay. There is no other option, and we have to include C and D. So C will be equals to C union C and D. Right. So here it will be C is AB union CD. Right. So it is ultimately consisting of ABC. So this is the vertex cover, right? This is the vertex approx vertex cover. This approx vertex cover, right? Now you see the how the structure is going on here. First we included AB. First we included AB, and this edge was considered. This edge was considered. Next we included CD. CD. This is AB. Next, this edge was considered, and then we are having this CD inside this set C. Okay. So you see here we are having 5 vertices. The vertex covered, approx vertex covered is ABCD, right? But you see the optimal vertex cover C star, say C star, optimal vertex cover is AC, either AC, or optimal vertex cover could be BD. This could be the optimal vertex cover, and this is the approx vertex cover. So this may not be optimal, right? Now another thing you notice that if I am taking the cardinality of C star, cardinality of C star is how much, can you tell me?
Sir, 2.
2. Who is telling?
Sir, Aditya Singh.
Hmm.
Sir,
Huh?
BD is not optimal.
Huh?
BD is not optimal because the edge AE is not being covered.
Yes.
Only
BD is
AC
not
is
optimal.
optimal.
AC is optimal. Very good.
Yes, sir.
BD is not optimal. BD means this edge I am covering, this edge I am covering, and with D I can cover this and this, and I cannot cover this. Very good. Yes. Who is telling?
Sir, Soham Dev.
Ah, very good. So C star is this is the optimal vertex cover. Okay. So perhaps I had that graph in mind, and then that graph I had in mind. Anyway, but it's a very good observation. So it's showing that you are following. Okay. So C star is cardinality is 2. And what is the cardinality of C? What is the cardinality of C? C consisting of A, B, C, D. Tell me, if C star is 2, then what is the cardinality of C? How C star is 2? In the set we are having 2 elements. In C, how many elements we are having?
4.
Huh? Hello? Where are you?
Sir, 4 elements.
See? Is this screen not visible? So this is C, I am telling C equal to A, B, C, D, C equal to this, A, B, C, D. So what is the cardinality of C? Aditya?
Sir, 4.
So why you
For
are
that.
not coming up? So 4
Sir,
elements,
2.
4. C star
Yes, sir.
2 elements, 2. So 8th standard guy can say. In 8th standard now people are who are giving JEE mains, they learn this set. Huh? Okay. Okay, so we have got, so you see this C star is 2 and the approx vertex cover is C, that is 4. So if I multiply the optimal vertex cover 2 with 2, I am getting 4. Okay. So this C, can I say that this whatever C, the cardinality of C, I'll be having the number of vertices, that will be less equal to 2 times the cardinality of C star. This example suggests that this is, okay, right. So this is whatever be the C star, cardinality of C star, that means optimal vertex cover. Okay, say the optimal vertex cover in some large graph, it is 10. Then our approximation algorithm is giving the guarantee that it will be finding one v prime with less equal to 2 times 10, that means 20 vertices. 20 vertices. We cannot write that C greater equals to 2 times C star. Then it will not be making sense. Because at that time I am telling that okay, our optimal vertex cover is 10, and then our algorithm will be finding a vertex cover which may be greater equals to 20. That means it may be 100 vertices. Okay. So then it will be way uh, separated than this C star. Okay. So it should be like this for the minimization problem. For the minimization problem, this we have to prove, or instead of C, instead of say this, what we have to say, this is we have done for approx vertex cover. We can do for traveling salesman problem. Okay, so our approximation algorithm, say we are naming it as A. Okay, our approximation algorithm. Then we can say the cost of our algorithm. So in our vertex cover problem, this is the cost is denoted by the cardinality of A. So we can write the cost of A, that we have to prove rho times the cost of opt. Okay. So this is the general statement we have to prove. And for our vertex cover problem, the cost of A is the cardinality of this algorithm. Cardinality of the vertex cover of this algorithm, say we are denoting by this. And rho, maybe in our vertex cover, it could be 2 or 1.5 or something. So if I am taking rho is 2 and the cost of opt, okay, so at that time it will be say C star. And the cost of A we can write also as we have given in the example, it is C. So you have to prove this. Okay. How can we prove this? Okay. Now the analysis. The analysis relying on this lemma. Okay. So this lemma is telling the approx vertex cover forms a maximal matching in the graph G. Okay. So whenever this approx vertex cover we have run, okay, on the graph, then we have seen that, okay, it is taking this edge with these two vertices, and then this edge with these two vertices. Okay. Right. And we had this original graph here. And this a maximal matching, the definition is a maximal matching is a matching that is not a proper subset of any other matching. Okay. Now, what is a matching? So matching means set of edges so that no two edges share a common endpoint. Okay. So here you see this edge. If I am having these two vertices and these two edges, okay, these two edges, then you see I cannot say that both are matching. Both are matching because this matching is sharing one endpoint this matching is sharing one endpoint this, and they are common. Okay. I have to include either this or I have to include that. Okay. Right. Either this or that. So that we have to remember that either I have to include this. If I am including this, I cannot include this because at that time they will be sharing a common endpoint. So the set of edges which are not sharing a common endpoint will be the matching. Okay. So this edge is a matching, this edge is a matching, and the maximal matching that is not a proper subset of any other matching. Okay. Say I am telling, say this is A, B, and this is C, D. And these, if I take any other edges here, okay, here or here, okay, then we will be seeing that they are having this common endpoints. Okay, so these edges these edges are the matching which are not subset of any other matching. But if I am telling that, okay, this is a matching, okay, this is a matching from this graph AB, right? But you see, I can include another edge like this which is also a matching. So this matching, if I am naming it as M1, and this matching if I am naming it as M2, then M2 is a proper subset of M1. Then M2 is not the maximal matching, but M1 is not the subset of any other matching. Okay, not the subset of any other matching. So that's why this M1 is a maximal matching. Okay. Now there is so this word you remember, maximal. Okay, maximal, not maximum. Okay. Now what is the difference between maximal and maximum? Right. So to understand this, let us take one more edge here. Okay, in this graph. Then you see that, okay, if I am including this edge with these two vertices, then this edge, say DF, so this is AE, this is DF, and this is BC. So you see, these are also a matching, and in this case, in this case, we are having, say this, we name it as some m star. We are having three edges which are matching. Okay, but look at this. Look at this thing. If I am taking AD and if I am taking BC, if I am taking BC, AD and BC. So you see, whenever I am taking AD, then this edge I cannot include, 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 because they will be sharing the common endpoint, and I am not doing that. Okay. Now BC, so this whenever I am including AD, that is not covering this edge BC. So BC can be taken in this matching. Okay. So this matching is the maximal matching. Say this is M prime. This is the maximal matching, but you see in the graph we can have more edges that could be matched also in some other way. So this M star is the maximum and this M prime is the maximal, right? So what we can say, that maximum matching is a maximal matching, because this matching is not a proper subset of any other matching. So that is, maximum matching is a maximal matching, but maximal matching may not be the maximum matching. Okay, right? And if you observe that our approx vertex cover, the way it is picking up the edges, either it will be outputting this or it will be outputting this. So that means our vertex cover is outputting maximal matching. So that is the observation that we have got, and that will be very much essential for further proceeding. Okay, now you see this. Okay, we had this graph. This is our original graph, okay. And we can, the way vertex cover is picking up the edge, then it could be having the structure like this, or it could be having the structure like this. Okay, right. So this could be, and you see that this thing, this structure and this structure is, we can say, the skeleton of this graph. Skeleton. This graph and say this graph. Okay. This is also a graph. May not have connection to all this. So this graph is a skeleton of this graph, because that whenever I am considering this AD, then I am removing all edges incident on both the vertices. So these we can think of as the skeleton of this graph. Okay. And any optimal algorithm must cover the skeleton edges, because we have seen that if I am covering these edges, then all the edges are incident on it, and there is a chance that we can cover all the edges in the original graph. So to get the lower bound, instead of thinking about this general graph, we can think of that The bare minimum criteria of the corresponding original graph is this, which is to be fulfilled to have any covering of this graph. Okay? So this skeleton graph, if I am taking into consideration, then we are done with the lower bound. Okay, we are done with the lower bound. So these edges must be covered by any optimal algorithm. Okay, because these are the bare minimum. These are the bare minimum, and that we have got from this maximal matching concept. Okay. So this observation is very important, right? And now now say we denote the set of edges by A, which are returned by this approx vertex cover. That means our algorithm. Our algorithm will be returning some edges that we have seen. Okay, if it is returning these edges, it will be returning some edges. It will be returning some edges A. So here, how many edges it is returning? It is returning AB, say AB and CD. So two edges it is returning, two edges. So that we are denoting by this set A. What is the cardinality of A? So we are having one edge, two edges. So two edges I am having. So what is the cardinality? The cardinality is 2. Okay. So this is one component, edge component, and another edge component is this. That means another edge is this. It is consisting of two edges. So that's why the cardinality of this set is 2, right? And
Sir,
uh,
sir, how can we prove that the algorithm is gives a maximal matching?
hmm?
How can we prove that the approximation algorithm gives a maximal matching for the graph?
No. This is, you see, this approximation algorithm, the way I am picking up the edges, okay, you see that the way I am picking up one maximal matching it will be given, right? So that may not be the maximum that you have got. So once our algorithm has picked up this guy, so what I am doing, I am releasing this edge, I am releasing this edge. So if I am doing this, then I am releasing this edge. Okay. So we have got one matching like this. And then whenever I am having this edge, whenever I am next, I have to consider this edge. Okay, because all the edges are removed. We have got this. We have to consider this edge. So it will be giving one one matching, and by the definition of the maximal matching, this will this will not be the proper subset of any other matching. Okay, because this edge, whenever I am considering, I have removed all the edges incidentally. Are you getting? So the
Yes.
construction of our algorithm, approx vertex cover, is giving the maximal matching, because that matching is no way the proper subset of any other matching, because no other edges are incident on this. In You may say that, okay, we are picking arbitrary edge in our approx vertex cover algorithm, right? We are picking arbitrary age. Then you can say, okay, first I am picking this age. First I am picking this age, then it will be taking this, and then all other edges which are incident on these vertices will be removed. So this edge, this edge, this edge, this edge removed, and then BD, BC will be taken. Okay. So AD and BC. Okay. So these two will also be a maximal matching. So the way our approx vertex cover algorithm is proceeding, that will not be the proper subset of any other matching. So that's why we can say that our algorithm will be definitely returning one maximal matching. Are you getting or not?
But sir, how can we show that it will not be proper subset of any larger matching?
No, that is by construction. Na? Whenever you are considering this age, you are removing all other. Na? So how can this be?
Yes, sir.
Are you getting? How can this be? We are removing all incident ages. Na?
Okay, sir.
Hmm. Okay. So we have got that was a good question anyway. This how can this be, right? So here what we are doing, or what we have done, okay, this is the bare minimum. Say this whatever our vertex cover is returning, that graph is the bare minimum skeleton of the original graph we had. Bare minimum, we had this graph, and this is the bare minimum criteria that we can have, okay, for running our optimal algorithm. Okay, that means this age is, because we have seen that this age is very important, because whenever I am considering this age and the vertices, all the edges which are incident on it will be removed. Okay, right. So instead of finding the optimal algorithm, instead of running our optimal algorithm, we don't know what is that optimal algorithm. Okay, for mind it. As a thought experiment, we have to think of that, okay, let us assume that there is one optimal algorithm. Okay. Then that optimal algorithm at least must have to be run on this bare minimum skeleton of this graph. Okay. So if we run this, and then uh, we will be forgetting this graph. Now we will be thinking that this is the corresponding skeleton graph of this original graph. And we are running our optimal algorithm so that these edges will be covered by vertices of this graph. Hello, হ্যাঁ ক্লাসে আচ্ছা হুম। Okay, so AB and CD, I guess C was here and D was here. Okay, so this AB and CD we are having. This is the bare minimum skeleton. And to cover the edges of this graph, can you tell me that if we run the algorithm, optimal algorithm here, then what we got to do if I am telling that, okay, to cover all these edges, at least one of the vertices, either A or B, C or D, we have to take into account. We must have to take into account because these are matching. Hello? হ্যাঁ আচ্ছা ওদের ক্লাসটা কখন 12টা থেকে তো ঠিক আছে 12টা থেকে ওটাকে একটু শিফট করো 12:30 এখন ওদের ক্লাসটা নিচ্ছি হ্যাঁ okay so this is a matching. So if I have to cover this age, if I have to cover this age according to the vertex cover definition and include into the vertex cover, then either this vertex will be there or this vertex will be there or both. As this is the optimal algorithm, we can think of that any of these vertex will be included in this optimal vertex cover. Okay, so how many edges we are having? The cardinality of edges 2. Now the optimal vertex cover must have, in our example, how many vertices? Can you tell me? Optimal vertex cover, the cardinality of optimal vertex cover. So that could be either A, AD, say, or BC, say, and any other possible. Okay, that means either I am taking A or I am taking this, and I am taking D, and B or C I am taking, B and D I can take. Okay, so what is the cardinality of C star? Can you tell me? Cardinality of C star? Cardinality of C star. Shoham, you tell me.
2.
So why are you not telling? C star is 2, right? So this the optimal algorithm, what we can say, this corresponding each edge we have to take one vertex. So that's why I can say that this optimal algorithm should be greater equals to this cardinality of A, okay. Cardinality of this A set, okay. Or you can take exactly A, right? So that means cardinality of A is less equal to this C star. Okay, I am exchanging position. Okay, so this inequality will be changing. So this is the lower bound we have proved for this vertex cover problem. This is the lower bound. Whatever optimal algorithm you can think of, at least these many number of vertices must be there in the optimal vertex cover. Okay. Now you see, observe what our algorithm is doing, our approximation algorithm. So our algorithm, what it is doing, whenever I picked up this edge, I have included both the vertices. Okay, both the vertices. So this cardinality cardinality of C, that means our algorithm, our approximation algorithm. Our approximation algorithm, the cardinality of C, that is the vertex cover returned by the approximation algorithm. The cardinality of C definitely will be 2 times the cardinality of A. That means whenever I am taking the edge, I am including both the vertices. So cardinality of A, if the cardinality of A is, that means 2 edges I am having. So corresponding one edge I am having 2 vertices. So the number of edges I am having multiplied by 2 will be the number of vertices here. So our approximation algorithm will be having C equals to 2 times the cardinality of A. And we have got a relationship with cardinality of A with the optimal vertex cover. So that is less equal to 2 times the cardinality of C star. So our approximation algorithm is, so we have proved that our approximation algorithm is 2 times the cardinality of C star. Okay. So this is how we have proved, right? So this is the way vertex cover is proved, that it is 2 approximation algorithm. Okay. So any question? So now you study